Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss problem solving on floating-point arithmetic operations. So, floating-point arithmetic, it is also known as real-point arithmetic. So, uses the numbers with the fractional parts as operands, and it is used in most of the computations. So, in a digital computer, the numbers are represented using two forms. The first form is the fixed point representation, and in the second one is the floating point representation. So, in digital computer, any number it can be represented using in any one of these two forms. The first one is the fixed point representation, and the second one is the floating point representation. So, in fixed point representation, the numbers are represented using fixed number of bits or digits, whereas in floating point representation, the numbers are representing as fractional parts. So, fixed point is used to represent integers. So, using the fixed point representation, we can use it to represent the integers, whereas the floating point is used to represent the real numbers. So, real numbers means here the floating point numbers are like 2.5, 4.8, minus 125.6. So, that means the numbers with fractional parts. So, in order to represent such type of numbers, we are using this floating point representation. So, usually the floating point numbers, they have a decimal point. They have a decimal point, and in floating point representation, any floating point number, it can be represented using three components, that are sign of the number, then mantissa, it is represented with M, and base B, and exponent E. So, this is a scientific notation of representing any floating point number. So, floating point number F is equal to M mantissa into base power exponent E. So, that is a representation of the floating point number. So, here for the binary numbers, the base value will be 2. For decimal numbers, the base value will be 10. So, in year 1985, the IEEE 754 standard for floating point arithmetic was established. So, using this IEEE 754 standard, the numbers are represented here, the floating point representation. So, coming to the problem solving. So, first question, let us consider that we have to add number A and number B. So, we have two numbers. The first number is A and second number is B. So, these two numbers are floating point numbers. So, already we have seen the floating point numbers are represented using mantissa into multiplied with base power exponent value. So, the first number mantissa represented with M suffix A, and base is 2, and the exponent of the first number is E1. So, its number is 0.10110 into 2 power 3. And second number is B. The mantissa of the second number is M suffix B, and base 2, and exponent of the second number is E2. So, here we are assuming here the binary numbers. So, that's why the base is 2. So, the second number is 0.11010 into 2 power 4. So, now we see how sub operations are performed in different stages. So, we will see stage by stage operations, how they are performing. So, during the first stage, stage 1, first exponent comparison will be takes place. So first one is the exponent comparison. So in order to perform addition or subtraction, the exponents should be equal. But here, according to this, the exponent of the first number is 3 and the exponent of the second number is 4. So because of the inequality, so we have to make it equal. The exponent should be equal. So first we are checking how many numbers are different. How much difference is there in their exponents? So that is with the mod of E1 minus E2. So exponent, first number exponent minus second number exponent. So that is equal to the exponent of the first number is 3 and the exponent of the second number is 4. So 3 minus 4, that is minus 1. So because of mod, we are taking only the positive value 1. And the stage 2 is the align mantisas. So align mantisas and choose the larger exponent as exponent of the result E2. So once we are comparing the exponents, then we need to align the mantisas, and we are considering the exponent of the larger number as the result of exponent of the result. So to make it the exponent of the first number 4, we need to perform 1-bit shift right operation, so that when we are performing shift right operation, the exponent value will be incremented by 1. So perform 1-bit shift right operation on mantissa of lower exponent and increment the exponent by 1. So if you perform 1-bit shift right operation on mantissa of the lower exponent number, so it will be a is equal to 0.0. So that means we are performing 1-bit shift right. So that means this 0 will move to after the decimal point. So it will become 0.01011 into 2 power 4, because when you perform shift right operation, the exponent value will be incremented by 1, so that 3 becomes 4. In the third stage, we need to add the mantissa. So first step is the exponent comparison, second one is the alignment of mantissas, and the third stage is the addition, performing the addition of the mantissas. So mantissa of the result will be, so this is the exponent of the first number and this is the exponent of the second number. So if you add, you will get this one. So 0.01011, 0.11010. So we are performing the binary addition. So 1 plus 0, 1. 1 plus 1, 0 with carry 1. So 0 plus 0, 0. 0 plus 1, 1. 1 plus 1. So 0 with carry 1. So 0 plus 1, 1. 1 plus 1, 0 with carry 1. So this is a result we got. So here, this one that represents overflow. So because the when you perform any operation, the result will be stored in the accumulator. But the accumulator cannot store this extra bit. This is called overflow. So to overcome that overflow problem, we need to perform a shift right operation by 1 bit. So once we perform the addition operation, addition on the mantissas, then we need to normalize the result if necessary. So the result of the addition is 1.001010 into 2 power 4. So since we have overflow problem, we need to perform 1-bit shift right operation. So once you perform shift right operation, then this 1 will move to here. So it will become 0.1001010 into, so when you perform 1-bit shift right operation, the exponent will be incremented by 1. So it will become 2 power 5. So after normalizing the result will be 0.1001001 into 2 power 5. So in this way, we can perform addition on any two floating point numbers. And coming to the second question, let us consider that we have to subtract number A and number B. The first number is given 0.11010 into 2 power 4, and the second number b is given 0.10110 into 2 power 3. Now we see how sub operations are performed in different stages. So this is similar to the previous one, that is, but here we are performing the subtraction operation. So first stage is the exponent comparison. So here the exponent comparison is a mod of E1 minus E2. So that is equal to mod of 4 minus 3, because the exponent of the first number is 4 and the exponent of the second number is 3. So 4 minus 1, that is equal to 3. So that means the difference in exponents is 1. That means we need to choose the exponent of smaller exponent number, and we need to perform 1 bit shift right operation, so that the lower exponent value will be incremented by 1, so that 3 becomes 4, so that the exponents of the two numbers will be equal. Then we can perform the subtraction. And in stage 2, align the mantissa. So align the mantissa and choose the larger exponent as exponent of the result. So because here the E1 is equal to 4, because the exponent of the result will be equal to the exponent of the larger one. So perform 1 bit shift right operation on mantissa of lower exponent and increment the exponent by 1. So this is the exponent, lower exponent number. So on that number we are performing the 1 bit shift right operation, so that it becomes 0.01011 into 2 power 4. Then in stage 3 we are performing the subtraction on the mantissas. Okay, so mantissa of result is equal to 0.11010, and the second number is the mantissa of the second number is 0.01011. So that if you subtract, you will get 0.01111. So if you subtract 0.11010, 0.01011. So in subtraction, if you subtract 0 from 0, you will get 0. If you subtract 1 from 1, you will get 0. If you subtract 0 from 1, you will get 1. If you subtract 1 from 0, you will get 1 with borrow 1. So according to that, 0 minus 1. So 0 minus 1 means 1 with borrow 1. So 1 minus 1, 0. 0 minus 1, 1 with borrow 1. So 0 minus 0, 0. So 0 minus 1, 1 with borrow 1. So 1 minus 1, 0. 0 minus 1. So 1 with borrow 1. Next 1 minus 0, 1. 1 minus 1, 0. So this is the answer. So 0.01111. After subtraction, the mantissa will be equal to this value. And in stage 4, normalize the result if necessary. So here there is no overflow, but here we have a underflow, because after the decimal point, if we have a 0 value, that will implies underflow. So in order to overcome this underflow problem, we need to perform shift left operation, so that this one will move to here, so that after the decimal point we don't get any 0 value. So that by performing shift left operation by 1 bit, we can overcome this underflow problem. So in a normalize the result, we are performing this shift left operation. So if you perform shift left operation, it will becomes 0.1111 into, so when you perform 1 bit shift left operation, the exponent value will be decremented by 1. So that previously the exponent will be 4. Now it becomes 3. So the result will be 0.1111 into 2 power 3 after subtraction. Coming to the third question, let us consider that we have to multiply number A and number B. So the first number given is 1.110 into 10 power 10. The second number given is 9.200 into 10 power minus 5. So the numbers are given in a decimal form. That's why the base value of the number will be 10. Now we see how sub operations are performed in different stages. So during stage 1, we need to add the exponents because we are performing multiplication. So in multiplication, the exponents will be gets added. So that's why the new exponent will be equal to exponent of the first number plus exponent of the second number. So the exponent of the first number will be 10 and the exponent of the second number will be minus 5. So 10 plus minus 5. So that is equal to 5. So that means the resultant exponent value would be 5. And during stage 2, multiply the mantisas. So during stage 2, we need to multiply the mantisas in scientific notation by hand. So how we will perform a general multiplication? In that way, we have to multiply these two numbers, 1.110 into 9.200. So it results 10.212000. So this is a resultant mantissa after performing the multiplication. So now, but here we are considering only 3 digits after the decimal point, so that we are rounding it to 10.212 into 10 power 5. Now in stage 3, we need to normalize the result if necessary, because here before the decimal pointer we have 10, but as per the scientific notation, before the decimal pointer we should have only a single digit. So that's why we are performing 1 bit shift right operation. So once you perform 1 bit shift right operation, so it will become 1 point. So this 0 will move to here. So 0212 into 10 power. So because of this shift right operation, the exponent will be incremented by 1. It will become 5 plus 1. So that it will be 6. Okay. So after rounding or truncation, that means after rounding, that means we are considering only 3 digits after the decimal pointer. So that the 1.021 into 10 to the power 6. So this is how we can perform the multiplication. And the last one is let us consider that we have to divide the number A by number B. So we are performing division operation on 2 floating point numbers. So the first number is given, so 0.2000 into 10 power 5, and the second number given is 0.8883 into 10 to the power of 3. So these two numbers are, 2 floating point numbers are given. We need to divide the number A by the number B. So during stage 1, we subtract the exponents because in the division the exponents get subtracted. Okay, so that's why the new exponents will be equal to first number exponent minus the second number exponent. So the first number exponent will be 5, second number exponent is 3. So 5 minus 3, that is equal to 2. Then we are performing the division on the mantisas. So if we divide the two numbers in scientific notation by hand, so 0.2000 by 0.8883, so it results 0.2251. So this is the resultant mantissa. So the result will be 0.2251 into 10 to the power of 2, because the resultant new exponent will be equal to 2. And during stage 3, the normalize the result if necessary. The result of the division is 0.2251 into 10 to the power of 2. So because here no normalization is required, because already the result is in a normalized form. So that's why no further normalization is required. So the result of the division of A by B is 0.2251 into 10 to the power of 2. So The slides are prepared from by referring the textbook M. Marismono, Computer Systems Architecture, Pearson, publication Pearson, 3rd edition, 2015. And also referred the another textbook, that is John D. Corpinelli, Computer Systems Organization and Architecture, publisher Pearson, 1st edition, 2001. So in this lecture, we have discussed how we can perform floating-point arithmetic operations on any two numbers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.